Okay, good afternoon to you all. And today we will be talking on a very interesting topic, which is what I call is the mysteries of our solar system. And in our solar system, two main objects which we will be talking today in this presentation are Moon and Mars. As many of you are aware that India has sent missions to Moon and Mars. So I would like to showcase to you that what type of scientific investigations has been done using the satellite data which we have received from the Chandrayaan-1 mission and the mission to Mars, which is popularly known as MOM or MOM mission. Okay. Just to give you a brief introduction of our solar system. So as all of you are aware, the sun is the star around which we are all evolved. And in our solar system, we have these four inner planets. One is Mercury, then Venus, the Earth, the Mars, and then there are two icy planets, gaseous planets, Jupiter and Saturn, and there are two icy planets, Uranus and Neptune. So these are the two, this Jupiter is the largest object of the solar system, followed by Saturn, Uranus and Neptune. However, all the four inner planets, they are much smaller in size, but their densities are much higher compared to Jupiter, Saturn, Uranus and Neptune. Apart from these major planets, we also have what we call as a dwarf planet. Many of you may be remembering that earlier Pluto used to also be known as a planet, but it got reclassified and now people are considering it to be a dwarf planet category. Then we also have remnants of a planetary collision between Mars and Jupiter in the form of asteroid belt. So large amount of asteroids are present between Mars and Jupiter, and which is supposed to be made by breaking of this Sirius planet which used to be there, but today we only have remnants of this. So there is a lot of interest today in studying first this small inner planets which are basically neighboring planets to Earth like Mars and Venus, and of course Mercury, which is much closer to Sun. So it is a very hot body. So in this talk today we will be just focusing on one of the satellites of the Earth, that is what we call as Moon, and then of course the Mars, which is being explored extensively by various space agencies, because the Mars has large reservoirs of water in terms of water ice, and it also has atmosphere, a very thin atmosphere, and people believe that the best chance to get life within our solar system can be on the planet Mars. So that's why there is a considerable interest in studying the Mars as a planet. Now as far as ISRO is concerned, you see ISRO has been very actively involved from its beginning in the core areas of research in space, atmospheric and planetary sciences. But the major emphasis in this direction came with the launch of Chandrayaan-1, the first satellite which ISRO has launched beyond the orbit of Earth. And that was in 2008. Almost we have completed a decade after that launch, and this satellite was supposed to make different type of measurements about the surface of the Moon. Then in 2013 we took a big jump and we launched the satellite called Mars Orbiter mission, which entered into which basically was an interplanetary mission. And these two satellites have given a large amount of data which we will be seeing in this presentation, which has basically resulted in many kind of new findings and discoveries about these two celestial bodies. Now as far as future plans are concerned, ISRO is already building, and then most likely in the first half of 2019 we will have a launch of Chandrayaan-2, which is a follow-on mission of Chandrayaan-1. Then we are also working on the definition of a follow-on Mars Orbiter mission, which is right now we are calling Mars Orbiter Mission 2, And we have also released an international announcement of opportunity for various researchers to participate in our Venus mission. So there is also a roadmap to go to Venus and study various scientific aspects of Venus. Okay, so that way you see we have a very active program currently as well as in the future, so that we can discover our own solar system and do new kind of discoveries and findings. Now we will discuss first about the moon. I told you that the moon was explored extensively with Chandrayaan-1 data. But why we want to study moon? What are the basic reasons, what are the basic causes that why one should study the moon? So there is a well-developed branch, what we call it the lunar science, like the way you have earth science. So the basic scientific interest is that how the moon has formed, what we call it the evolution of the moon. So how the moon has formed, how the planet has evolved over a period of time, what kind of environment is there on the lunar surface. See, we know that on Earth we have an environment which is quite friendly for the survival of life. But do we have the similar luxury on moon? Do we have atmosphere? And do we have the sufficient amount of gravity? What type of temperature regime is there? All those things are important, as far as the future colonization of these planetary bodies are concerned. What type of solar radiations are coming on the surface, whether we will need some protection if humans land on moon. All those issues are basically addressed under this broad theme of lunar environment. Then you will see that moon also has large amount of impacts which are caused by the meteorites. So it is a collection of solar system impact records, and a large amount of information can be derived using or by studying the solar system, by studying the impact records to understand the evolution of our solar system. So these 3-4 major scientific themes are deriving our quest to explore moon. Now I will just tell you in very brief, what were the scientific payloads which were there on this Chandrayaan mission. So a satellite basically is like a bus, and on satellite you will have different type of sensors. So here on Chandrayaan-1 we had 11 instruments from different countries, and using these 11 instruments, different type of scientific objectives were supposed to be met. So as I told you, there were payloads from 10 different countries on the mission, and the most important ones were terrain mapping camera, which was a high resolution imaging camera developed in India to image the surface of moon at 0.5 meter spatial resolution from 3 directions, so that you can build the topography. Then you have another instrument which is called the lunar laser ranging instrument. This is a laser ranging instrument where a laser pulse is sent towards the moon surface, and the two-way return time is then used to compute the elevation of that particular location. So if the two-way travel time is more, that means the pixel is steeper, and if the two-way travel time is less, that means it's an elevated area. So using this data also, global topography of the moon was reconstructed. Then we have this important spectrometer from NASA JPL and it was called Moon Mineralogy Mapper, M-Cube. This was basically a hyperspectral instrument which operated from 0.3 to 3 micron spectral range with a spectral resolution of the order of order of 20 nanometers or so, and at certain locations it was 40 nanometer as well, which this was primarily to study the moon in hyperspectral mode to get information about the minerals or the composition of the moon surface. Similarly, in X-ray part of electromagnetic spectrum, we get the information about the elements which are present in a terrestrial body. So if you use X-ray fluorescence during an active sun, so the fluorescence as a function of wavelength So for different wavelengths you will get peaks of emissions by different elements. So this particular instrument was used for elemental abundance along with the high X-ray spectrometer. Then we had this mini synthetic aperture radar, what we call the MINISAR. So MINISAR is an active sensor which operates in the S band of electromagnetic spectrum. Main purpose of this instrument was to study the areas on the moon which were permanently shadowed. So there are regions in north and the south pole where the sunlight does not reach because they are on the poles, and many of them are deep impact craters. So if you do not have sunlight, you cannot do the passive remote sensing. So in that case, one needs to have an active sensor, and this MINISAR was used to find out for finding out the buried ice, which people think that it can be there in the polar regions of the moon surface. Similarly, the hyperspectral imager, a HISI, was built in India, and this has a spectral range from 0.3 to 0.8 micrometer. CERT2 was a German spectrometer which was non-imaging, and it was operating from 0.8 to 2.5 micrometer spectral range. And there were two other small instruments to analyze the radiation, doses, which the amount of solar radiation which reaches onto the moon surface, as well as the reflected radiation, the reflected solar wind was also measured from the instrument, a Swedish instrument called SARA. So as far as you can see, there were 4 or 5 remote sensing instruments which are supposed to study the surface and morphology, topography, as well as composition on the moon surface. So what were the major scientific achievements which we got? So I will show you examples of these 3 of highlights which were scientific highlights which were there from the Chandrayaan-1 mission. So the first and the very most important finding which Chandrayaan satellite made was that it established that there is an active but tenuous means very weak, very thin, hydrosphere around the moon surface. You know about the hydrological cycle on Earth. That means there is a moisture in the water which is there in the oceans, and with the help of sunlight, the water gets evaporated, and then it lifts up into the upper atmosphere. The condensation happens, the cloud nuclei clouds forms, and then clouds, when they become too heavy and too cold, they precipitate, and then rainfall occurs, and the rain basically drenches the landforms, and some of this rain goes into the interior of the earth, as well as some part of it goes as runoff again back into the sea, and this process continues. So this type of cycle is called hydrological cycle. So on moon, previous thinking was there that there is no water or no water molecule, water of any type present on moon. However, with the Chandrayaan-1 observations, it was proved that there is an active hydrosphere. That means not only there are water molecules, but there is a cyclic process of production of these water molecules on the lunar surface. Similarly, it was established using the observations from Chandrayaan-1 that the moon is volcanically active and geologically dynamic, which earlier thinking before Chandrayaan era, the thinking was that there is nothing much happening in terms of volcanic and the active tectonics on the lunar surface. So this myth was also broken with the data which we got from Chandrayaan-1. And then as far as the moon's evolution is concerned, there was a hypothesis which used to be called as global magma ocean hypothesis, and that is how the moon's evolution was explained, and we could get evidences, or what you say, the experimental proof to prove this hypothesis that yes, the moon was formed due to a process what we call as the ocean global magma ocean. What does global magma ocean means is, in a very simple terms, if I have to tell you that the primitive moon, the moon which basically formed out of a bombardment with the earth's surface, was very hot, and then going around the earth, and slowly and steadily it was becoming cooler and cooler. So so from molten stage it was getting into the solid state. And what happens when any material or elements which are there in the molten state, because of the gravitational attraction towards the core, the heavier elements will sink and the lighter elements will float. And when they cool down, the crust formation happens for a planetary body, and the crust will always be made of the lighter elements compared to the upper mantle material, which basically is supposed to be made of the heavier elements like magnesium, iron, nickel, cobalt and stuff like this. However, the surface or the crust should be of lighter elements like silicon, nickel and aluminium and stuff like this. So this was confirmed when using the spectroscopic observation from Chandrayaan-1. We proved that yes, at many locations on the moon we could find evidences of the this lighter crust, which geologists basically they call such type of rocks as anorthositic rocks. So we find large amount of anorthositic rocks all across the moon surface. So that led to establishment of what we call as the global magma ocean hypothesis of lunar evolution. So these were the three major scientific findings which we can say that if I have to summarize, we can summarize that this is what we achieved, and these three findings, they changed our perception about the way we think about moon surface. Now I will show you the details of each of it. First we will discuss about the hydrosphere on the moon surface. So before we go to that, I just would like to show you the snapshots of both the sides of the moon. The side which we see from our our planet Earth, this is the one over here, and as you can see there are dark patches in the near side of the Earth. This big large basaltic plains are basically called mares. They appear dark in color because they are composed of rocks called basalts, which essentially absorb the sunlight, so they are much darker compared to the lighter rocks which are basically anorthosites onto the moon surface. Another interesting thing what you can observe is that moon surface is heavily cratered. There is large amount of impact craters are present. It happens because the moon does not have an active atmosphere around it. So since there is no atmosphere, most of the meteorites which are basically coming to our moon surface, they directly hit the moon surface without disintegrating, unlike Earth. So what happens in case of Earth, we have a dense atmosphere. So any projectile which is coming towards Earth with a large velocity, faces resistance with respect to the air molecules, and then the resistance becomes very high, and many times the meteorites breaks away or it burns out and breaks into small fragments. So large impact craters are not forming on Earth, even though there are impact craters, but their density and the number of impact craters are much lesser compared to the moon surface, because moon does not have atmosphere around it. Same way, this side of the moon hemisphere is called the far side. This side we cannot see from Earth because we are tidally locked to the moon. That means the moon goes around the Earth in same time the time it takes to rotate on its rotate on its axis. So the rotation time and the revolution time around Earth is same. So considering that phenomenon, you can never see the backside of the moon from the Earth. So this backside was first time mapped from a mission called Clementine mission in 1994. So as you can see, there is a remarkable difference between the near side and the back side of the moon. Near side has this large amount of dark patches, but on the back side you have the number of dark patches are relatively lesser. So this problem of skewed distribution of basalt plains on Mars is called back and front asymmetry. That means there is an asymmetric distribution of basalts on near and back side of the moon. And people also try to understand that why such type of things happen, why the basaltic plains are not evenly distributed on both sides of the moon. Another interesting thing is that the lunar resources is also becoming important. The moon is made of mainly igneous rocks. since there are no weathering agents, you do not have sedimentary rocks over there. However, at certain locations you can find metamorphic rocks, which basically do get produced with the impact craters, because the impact craters bring large amount of kinetic energy which changes the rock forms and the rock types. So metamorphism of that nature is possible on the moon surface, but most of the lunar material is igneous in nature. We need to map these resources so that in future, if we want to colonize or if we want to go to moon and use these resources, we are sure that where we have to land. Now, as we were talking about the impacts, you see on moon there are large amount of impacts, and this slide shows you a process of impact cratering. So this is a meteorite, it has just touched down, it has touched the surface of the moon. Then as soon as it touches, because it comes with a large amount of velocity and it is quite hot because of the heat which it carries, and when it hits the surface there is large amount of friction is produced. So a transient cavity is formed. So this is the cavity in the surface which will be formed, and the material will be thrown out. So this is material which is thrown out is known as ejecta. So this material can go and splash up to thousands of kilometers depending on the magnitude of the impact, and then within no time you will find such type of impact craters forming. So if the impactor size is larger than 80-85 kilometers, many of these craters will also have this central bulge at the center, and such type of craters are called complex craters, which essentially develop this type of central bulge. So here in this chart I am showing you the classification of the craters. You have very small micron size craters, the pit craters, and then you have craters which are of the order of diameter of 1 kilometers, then 28 to 30 kilometers. They are basically the complex craters, more than 30 kilometers radius. Then you have peak ring basins which are of the order of hundreds of kilometers, and then around thousands of kilometers size craters are called multi-ring basins. Okay, so here I will show you some observations of the crater photographs taken by Chandrayaan-1 mission. So this is a impact crater which has a diameter of roughly 5 kilometers from here to here, and then you can see the terrace structure over here, and the ejecta material, which is dark here in this case, is also splashed around this particular crater. And you also have this ray craters, which are basically the smaller craters. Then this is an example of a complex crater. This crater is there in the southern highland of the moon. You can also see with a good binocular on a full moon day from Earth itself. And this crater is named as Tycho crater, and this is the image of this full crater, and this is the central peak. This central peak has a height of around 2 kilometers, 1.6 to 2 kilometers, and this is the three-dimensional picture which we have generated using our Chandrayaan data of this central peak. So as you can see, it's like any other peak which you find in any elevated region like Himalaya or any other mountainous region on Earth. However, you can see there are traces of large amount of debris flow on the slopes. There are certain accumulation zones over here, and then the floor of the crater is also seen very clearly, where you can see certain rupture zones, or what we call as the cracks on the floor of the crater. So what I want to show you is that the imaging at very high resolution can help you in identifying various morphological entities on the surface of moon, and then you can interpret this data to find out large amount of scientific inferences. This is another very interesting example, again on the rim of Tycho crater over here. So you can see that there is an impact crater. So what happens when impact happens suddenly, because of the heat, the parent material will get melted, and then this melt, or what we call as the impact melts, these impact melts will start flowing with the gravity of the earth, of the moon, which is 1/6 of the earth. And so slow flows will always get created, and in this particular feature you can see that there are wave patterns which is basically associated with some kind of flow patterns, and these flow patterns have basically got frozen in time. You can see over here, and then some of this impactment material has again flowed onto the slope up to this extent, but most of the material was basically confined to this region, and some of it can go further down. So this process is one can say that the history or the early solar system history is preserved on the moon surface in terms of melt ponds and in terms of impact melt records. Now there are another interesting features which you find on the moon surface, this type of sinusoidal features, and these features are called rilles in Latin language. They appears like rivers. So this is a these are basically not rivers of water, but they used to be old rivers of the lava flows onto the moon surface, and once the this surface has cooled down, most of this basaltic material will collapse, and this type of the three-dimensional drains will get produced. So if you see carefully, this is the lower topography and this is the higher topography. So it's a three-dimensional cave-like structure continuing up to here, but at certain location the uncollapsed lava tube or the lava tube has not collapsed, so you have this roof-like structure also. So this type of features are very good hiding place for any future human explorers, so that they can be shielded from the harmful radiation of the sun which are impinging onto the moon surface. Now, having told you very briefly about the images which we got and then type of interpretation which can be done, I would like to draw your attention towards another interesting science of spectroscopy, through which you can basically find out the composition of the surface material. So as I was telling you, you have mostly the igneous rocks present onto the moon surface. There is no soil, there is no overburden, there is no vegetation. So the rocks or the igneous rocks are exposed. So these are the spectral absorptions. If you study the hyperspectral data sets, you will find in various igneous rocks. So you have different type of pyroxenes, cyanopyroxenes, orthopyroxenes, you have olivine, you have plagioclases. So all these type of minerals which are some part of rocks assemblages have their own characteristic absorption features. See, like pyroxene will have absorption, first absorption at 0.98 micron, and there is a secondary absorption around 2000 nanometers. Similarly, the olivine will have a deeper absorption line at around 1.1 micron, and the secondary absorption is much weaker. So if you find per pixel this type of spectral distribution, for those pixels or a group of pixels, you can classify them as a one composition unit. So using three hyperspectral imagers, the composition map of the moon has been generated. So this is a global composition map of the moon. All these red regions here you see are basically highland rocks or the the anorthositic bright rocks. Then this you have basaltic rocks, as I was telling you, but within basalt also, depending on the evolution of the basalt, the composition of the basalt will also be different. So blue color represent the basalt rocks with pyroxene, and the green color represent the basalts with olivine over here. So you have within basalts a variability which basically is an indicative of the evolution process of moon surface. The another interesting thing which people reported using hyperspectral data is that hydrated moon. That means the moon has water. So this map was produced using Chandrayaan observations, where all these blue and the cyan color regions are basically regions which are supposed to be rich in water molecules compared to the equatorial region over here. So the basis of these findings was that using this spectroscopic observations, the water has an absorption band at around 2.9 micron or 2900 nanometer, and the hydroxyl molecules also, ions also have this absorption between this range. So if you are getting a broad absorption between 2800 to 3000 nanometers, you have a sufficient evidence that the water molecules or the ions, hydroxyl ions will be present at that particular location. So the same thing was done. These are the spectras in different wavelength regions going all the way from equator. This is equatorial data, and as we move from equator to pole, they found that the absorption lines becoming stronger and stronger. So that means that if you have this absorption coming over here from 2800 nanometers and then going strongly up to 2900 nanometers, you have sufficient evidence for the presence of water or the hydrogen bounded hydroxyls ions in this region. So that is how the famous discovery was done of water on the moon, and that global moon maps were global water maps on the moon were prepared. So all these blue regions basically showed up this type of absorption features compared to the the yellow and the green regions on the moon. Okay, so this initially such type of observations were limited to polar regions. However, later on some of our colleagues and our scientists here in India also found that there are certain features which are not in equatorial region but in polar region, where also we do absorb this type of absorption features, and this type of water absorption features were called endogenous features. That means this water is trapped in the crystal lattice structure of the lunar rocks itself. It is not coming out through some cometary impacts or through some solar wind interaction processes. Yes, the same thing, this region where we got this type of anomalous distribution is called Compton-Wilkovich region, and these are the spectral absorption curves of this particular area. So coming to the third major important item is like volcanically active and geologically dynamic moon. Large amount of observations previously were there which were suggested that the lunar basalts were old, less than 4 to 3 billion years, and then it was thought that moon is volcanically inactive. There is no sufficient internal heat left in the planet to have a plate motion like the one we have on Earth, and virtually nothing is happening onto the moon surface. However, the results which we obtained from Chandrayaan-1, then subsequently a high resolution data came from Lunar Reconnaissance Orbiter, LRO mission, and then Japanese mission was also providing lot amount of data. It's called Selene or Kaguya mission. So all these data set went together and were analyzed. This perception changed, and we started getting evidences of very interesting features like this, where we have seen that there are fresh exposures of volcanic activity onto the moon surface. I will not go into details of this, but what it shows you that there are boulder movements, there are impact craters, there are craters on which the secondary flows are there. So all these evidences points towards that moon is not yet geologically dead. There is some activity which is there, which is of course not very as drastic as what we have on Earth, but there are subtle changes which are happening onto the moon surface in terms of geological context. Then having told so many things about lunar surface and findings which were made about the moon, still all the mystery of the moon have not been resolved. There are large amount of things which are yet to be ascertained, and one important thing which we still need to understand, that this volatile material or the water, let us say, if at all it is present, what is total amount, how we can quantify the total water present in the polar regions or in the equatorial regions, whether this water can be extracted for our utilization purpose or not, what is its abundance, in which area it is more, in which area it is less, and what is its origin, whether it is a cometary origin or it has been basically there in the lunar rocks itself, it has come from somewhere outside, we do not know. So whether this water, if we exploit, is it renewable like the one we have on the Earth? You have the riverine systems where water is available on a seasonal basis, so at least in the season you have large amount of waters, you can fill reservoirs, so that renewability is questionable. So whether it is a one-time process or it's a process which repeats itself, that's a question mark. Nobody knows it. Similarly, the internal structure of the moon is also not very well defined because we have not put up a geophysical network over there. So these are all things which people are trying to understand by sending now the advanced missions These advanced missions are not only orbiters like Chandrayaan-1. We had a satellite which was orbiting around the moon surface. We want to now land onto the moon surface. We want to put landers, and then landers will carry rovers. These rovers can be controlled remotely from Earth, and they can roam onto the moon surface, at the same time do certain scientific experiments. So India is planning a next follow-on mission of Chandrayaan-1, which is being called Chandrayaan-2, and this will be a 3-tier system. There will be an orbiter, there will be a lander, and there will be a rover. So you will do a lot of scientific experiments from 100-kilometer orbit above the moon surface. Then you also have lander, which will land and then to make in situ measurements on the various aspects of moon surface like temperature, pressure, thermal conduction, and lunar quakes also we are thinking to study. Similarly, there will be a rover which can go to different places. There are instruments which have been put on this rover. Mainly they are supposed to tell you the composition at that location. So one need to do a very good thorough job on the landing sites. So once you know what type of variability exists in your landing site, that can help you in path planning of rovers, and then bringing out maximum science with minimum number of observations. So now almost we are into the almost final phase of Chandrayaan-2 mission. In the first half of 2019, the mission is likely to be launched, and we are all eagerly waiting for this satellite, so that further understanding about the moon can be generated. Okay, so this is how the Chandrayaan-2 mission will look like. There will be an orbiter, there will be a lander sitting over here, and from lander a small rover will come out and it will start roving onto the moon surface. These are the instruments on Chandrayaan-1 2 payload. I told 11 were there in the first case, but now we have more scientifically oriented and heavier sensors. So we have 5 on the orbiter payload, and since the orbiter will also carry the lander, we cannot have many payload, because the lander itself is quite heavy, and then there are rover within the lander. So there is a you have to have only the optimum number of instruments in the orbit. So we have Chandrayaan-2 large area soft X-ray spectrometer, L and the span. This time we are going to put dual frequency SAR, and then imaging infrared spectrometer, which will go beyond 3 micron, that limit which was there in case of moon mineralogy mapper. We are going to break that. So we have first time observations on moon up to 5 microns, which can tell you a lot of things about the reproduction cycle of water onto the moon surface. Then you have this terrain mapping camera which was there. We are repeating it because we could not have the full coverage of lunar topography. Then there is another interesting instrument to do in situ measurements of tennis atmosphere of moon, or what type of elements are present around the moon surface in the atmosphere, or what we call as the exosphere. Similarly, the lander will also carry 4 instruments. We will have a seismometer in this lander which will be deployed, and for a mission period time of around 1 moon day, which is equivalent to roughly like 15 days on the Earth, this seismometer will be active because it needs power, and if the sun is not there, you cannot provide the solar batteries onto the rover, onto the lander cannot provide the power, so you cannot retain or cannot operate the seismometer. So we think that probably it may last for 1 lunar day, and we should be extremely lucky to get some moonquakes if at all we get during this period. Then we have another instruments called CHEST. This is a thermal instrumentation which is supposed to measure the heat flow, the amount of heat which is coming out of the moon surface. Then there is a Langmuir probe. This is a probe basically which measures the plasma densities. Plasma is emanated from the sun, and then it travels up to the moon, and since there is no magnetosphere around it, it can come and hit the moon surface. So we want to study the solar wind and then its interaction process at the moon surface using this Langmuir probe, which can give you the plasma densities. And then you have this dual frequency radio science measurements to measure the total electron content in the ionosphere of the and the moon surface. So the rover will have two very simple experiments called LIBS and APEX. Both the experiments are supposed to measure the elemental abundance of the moon surface, but using two different techniques. One will use laser to break down the surface material, and then a temporary plasma will be generated, which will be used to study from a spectrometer. Similarly, the alpha particles will also be used to study the composition of the ground composition of the lunar samples over there using the rover data sets. So this was about the moon. We have not left with much time. Maybe very quickly I will just show you the Mars MOM results. So we will not discuss much about the Mars, but Mars is the planet which is supposed to be very interesting, since it is close to Earth. It has seasons like Earth. It has the same day length as we have on Earth, and it has resources in terms of water and water ice. This picture shows you the north polar cap of Mars, which basically is nothing but made of water ice, and during the summer period a large amount of sublimation happens from this north pole of Mars, where the water molecules does not flow like water, but they simply become gas molecules. So there is a transition from solid state to gaseous state, and that process is called sublimation. So Mars has been extensively studied by various international agencies. We will not go into details of that. This was the Mars mission. It was launched in 2013. Lot of earthborne experiments were done, and finally an orbit of 372 by 80,000 kilometers were achieved in 2014 November. And then the orbiter start going into the highly elliptical orbit around the Mars surface, and it has this is how the spacecraft looks like. This is the antenna to communicate with Earth, and this is how it looks when it was ready to launch. It is on the spacecraft, and the liftoff happened on November 5th, 2013. So this was the journey. This is Sun here. So once you have this Earth burns, put the satellite into this orbit, and this is called the heliocentric phase, where the gravity of the Sun will be used to go down all around the Sun, and this was the location of the Earth at that time. And then the Mars was located over here in the planetary system, and then the Mars was coming in this orbit, and the satellite was coming in this orbit. Then they became, they came very close to each other, and then some velocity reduction exercises are done, and this is called Mars orbit insertion, and the satellite will get captured by the gravity of the Mars. So this is how the entire journey of 299 days has been summarized in this picture. Okay, so these were the 5 instruments, where there was a camera which is called Mars color camera. Then there was a thermal imaging spectrometer to do the analysis of temperature data in different wavelengths. Then methane is another interesting thing which people are trying to find on Mars. So there was an instrument to find methane on Mars, and then there was another instrument called Lyman alpha photometer to measure what we call as the escape rate of hydrogen in the atmosphere of Mars. I will not go into details of this lab. And MENCA is another spectrometer which is supposed to give you the neutral composition. That means neutral atoms which are there in the atmosphere. How does they get distributed with the vertical structure in the atmosphere on Mars? That knowledge can come from this MENCA mass spectrometer. Okay, so this was the orbit. As I told you, we went into a very highly elliptical orbit. The periapsis was roughly around 370 kilometers. The apo was 80,000. So if you are here in this orbit, you can see the full disk of the Earth, of the Mars, and when you go very close to the Mars, you can do high resolution imaging of the Martian surface. So using this concept, large amount of imaging was done. This is a beautiful full disk snapshot of Mars. You can see in one snapshot itself most of the morphological elements of Martian surface. You have the beautiful ice caps, the dust storm coming out, the dark basaltic terrains, the red color oxidized surfaces, and of course some kind of waviness in the atmosphere on the peripheries on this edge. And then there are some hints of white tinge, on the southern tip of Mars, which is essentially to the polar caps at the south pole as well. So similarly, there were many occasions when the full disk of the Mars was captured, and it shows distribution of Martian clouds, haze, as well as dust storms in the atmosphere of Mars. There is another interesting feature on Mars called valleys of Marineris. It's a long gorge. The gorge runs up to 4,000 kilometers in length, and then it has a width of around 200 kilometers and a depth of more than 10 kilometers at many places. And most of the time it will get filled with the dust in the atmosphere, and you will see a bright reflected radiation coming out of this gorge or canyon, as you understand in geological terms. This is again a high resolution picture of this canyon. You can see now the exposed walls of the canyon. This image was taken at around a resolution of 300 meters from an altitude of 5,800 kilometers. So similarly, there are very interesting features on Mars we could capture. This is a dust storm, this is a dust twister, and you can see the same area on different dates. One area showed you the dust storms, and then after some 8 days or so, the dust storm has vanished. So you can see the surface features now. So this tells you that Martian atmosphere is pretty dynamic. The dust storm keeps on happening. Dust on the Martian surface gets lifted by the atmospheric circulation, and then dispersal and the deposition also happens in a fairly rapid time. Then another beautiful observation on the clouds on the Martian surface. This is the volcanic, three complex volcanoes over here. This is called the volcanic complex, and then this is the largest volcano in the solar system called Olympus Mons over here. So you can see the formation of condensed clouds at the hilltops of this mountainous regions on the Martian surface. This is another high resolution picture of Olympus Mons. So you can see the caldera, where caldera is the place from where the lava oozes out when the volcanoes are active, and then these are the the flanks of the volcano, and then this white thing is nothing but the condensate, which is a water vapor condensate, which happens at this altitude. The height of this volcano is around 25 kilometers or so, which is more than 3 times than the height of Mount Everest on Earth. So you can imagine that on Mars large volcanoes are there, which probably has led to the cooling of the planet in a rapid manner. And today the internal structure of Mars does not support magnetic activity like global magnetic activity, which basically says that the core has solidified, there is no liquid left. That's why there is no convective activity, and the global magnetic field is not there. Another interesting thing on Mars people have found are the evidences of water flow. So this is a very nice geomorphological evidence. If you see this trace, it appears like channel bars on Mars surface. This cross cuttings of impact craters. You see, this is a crater. The wall of this crater has been eroded with the flow of water. So many such observations are there on the Martian surface, where we have large amount of evidence in terms of morphology as well as in terms of mineral presence. We find alternated minerals on Mars, minerals which are basically clays, carbonates. They only form when water is available, otherwise the formation does not happen. And we find today the evidences of these minerals on Martian surface, suggesting that once in some time in geological history there was liquid water onto the Martian surface. This is the ice cap. This is a mosaic of the ice cap of the Martian polar cap, the northern polar cap on the Mars. So this is what just wanted to share with you, that how does Mars look like, what type of observations was made by MOM. There are other observations by different other payloads, so we will not have time to discuss. We only showed you the remote sensing observations through imaging cameras and spectrometers. So what is up? What is next? Well, next is that we are now, with the excitement which got created because of this mission is not going to subside in future also. We are planning and working on a more scientific mission definition to a follow-on mission to Mars, which we are calling MOM-2, which we have a plan to launch it by 2020 or 22 time frame, and the selection of these payloads have already under process. Similarly, a mission to Venus is also being contemplated, and mostly by 2023 we will have a mission to study the Venus and its atmosphere. I will end with showing you this postcard from Mars. It's a very nice, interesting picture. It resembles like a bird over Earth. Many of you must have seen that bird. It's found in southern hemisphere, in Australia and New Zealand, and in Antarctic it's called kiwi. So you can see the beak of the kiwi and an eye, and then some internal compositions. But this is nothing. It's a volcano on the Mars. It's a geological structure which is has lot of evidences of tectonism on its surface. You see, this is the remnant position of the volcano. It appears that it is shifting in this side, which also is seen from this shrinkage. And then this caldera, or the mouth of volcano, has also been collapsed. Ideally it should be a symmetric body, but there is a lot of asymmetry over here, and there are impact craters, they just has happened subsequent to the formation of volcano. So we have a compilation of such type of interesting images, and the images which were captured by the Mars Orbiter mission, and most of these images has been put as a compilation or a collection in this atlas, what we call as the Mars Orbiter Mission Atlas. And this, if you do Google from your internet, you will be able to download the PDF version of this Mars Atlas from ISRO's websites, like ISSDC website in Bailalu, which is a Space Science Data Center, and most probably from Space Application Center website also. You should be able to download this atlases. With this, I think we have come to the close of this talk, and I would like to thank each one of you for your kind attention. Thank you very much.